I think those are the ones I fucked up. Yeah. See, I wasn't sure about that.
It wasn't one of
All right, everyone. Is it a no-show Friday or a slow-show Friday? Late already. Let's go ahead and get going. Hey, whoa. Really, stop now. Okay. Like that. Anyway, so I don't know, class business, not much to say. Next Friday's your test. Double lecture today, so that way we can review Wednesday. We are exactly on schedule on the calendar. If you're following the calendar meeting, that's great. If not, you're probably going to be fine. I did write the test. I wrote half the test last night. So let me go ahead and tell you, I definitely saw. You guys are from the same class? Yeah, okay. Did you tell that person to let you out on time? Had an exam? Oh, okay. Well, no, they let you. Tell her to give you less time. Okay, so class business, so I did halfway, excuse me, I did halfway write the test. I definitely biased it towards derivations. So just heads up, that's the last problem set. Or was it this problem set? Which is the one with a lot of derivations? Last one, right. All right, so very biased towards that. I definitely have a lot of, the questions I ask generally focus on entropy, especially like derivations involving entropy, and I do have some bits like the dt, dv at constant s, right, the adiabatic, reversible, dp, dt, and all that, dp, dt at constant s. So that is definitely represented on the test. Now the cheat sheet, let me give you a heads up, and I know what I'm talking about, I'm writing it. Cheat sheet, I wouldn't look at it, the cheat sheet can be like much more important than normal. I wouldn't look at it and try to reverse engineer what's on the test. It's not really a smart thing, and trust me on that, or you can try it, doesn't matter. But what I want you to do is when you get the cheat sheet next Wednesday, is just make certain you know what's on it. Just be familiar with it. All right, so that is a big hint that maybe there's things in there that are like, oh, I need to take that from the cheat sheet and put it here. Okay, big hint, all right? So just familiarize with it, but when you try to reverse engineer my test, it's not going to be easy. It's not possible. The test is definitely, I took just, before I say the next thing, let me point out that we've been kind of in this continuous gas expands, gas contracts mode up until really today. What song is that? It's terrible. Actually, I like the ringers that are like, you know, it's like when I was a kid. We actually only had rotary phones when I was a kid. That's how old I am. But, how old am I? Am I here? Anyway, so I'm sorry, I'm off track. What else was I going to say? Now I got off track. See, you shouldn't let the phone ring. I was talking about the test, and so you know, we have been on this continuous gas expands, gas contracts, give me Q, W, H, U. So there's more material, and it's all kind of one thing up until today, where we're really going in a different direction as of today. So that means that the test is just, let me just straight up say, the test is harder, okay, than the last one. Again, by virtue of just the fact that there's more material that all ties together. That does not work in your favor. All right, but at the same time, you've had lots of problem sets and lots of examples, and you have me spilling my guts. That's in your face. So I think you're going to do fine, but it's a little hard to imagine you're going to blow out this test like the last test, but then prove me wrong. And even if you don't, that's fine. You did really well on the last test. It'll balance it. And then you got a third test in the final review. So again, all right, I'm babbling too much. We got to get into new material. Wednesday, so we're taking a major left turn here. I'm certain I will find a place for it on the test. But remember what happened last time when we did Carnot and entropy, right? Now, you saw it on the test, but how much was it? Just like 2 questions, right? Like a true and false question, and I had one other spot. Right, so that's kind of what I'm leaning towards now in terms of material we're going today. I want you paying attention, which is why I was going to put it on there, but the material today and Monday probably will not be a very big part whatsoever of the test. What question, there are some numerical questions I can ask, and I'm going to get to 2 of them today. If I do have it on the test, I'll provide an example on Wednesday, the day of the review, of the type of question I might ask from today's and Monday's material on Wednesday. But I haven't written that part of the test yet. I don't know. Okay, so anyway, I'll tell you more on Wednesday. Does anybody have a question? Any other class business? We're okay? But, all right, we're okay. All right, folks, complete turnaround of what we have been doing. Liquid mixtures. Okay, so OCD. All right, this is going to be just shockingly different than what we've been covering, so just understand that. Now here's another bad thing. As I mentioned to you before, today is the day you're really going to see it. When we've been doing DHDV at constant T and using the perfect gas law for which you get 0, those derivations are perfect. There's nothing wrong with them, except, okay, the perfect gas law isn't really correct, but at room temperature pressure, it's actually really pretty accurate for just about anything. The errors are pretty negligible. It's only when you get to extrema that P equals RT doesn't really work. So this has all been perfect. It's exact. And you test it under reasonable conditions, you find that you're right. To a small percent error, which is why real gases are not perfect gases, to the point that hardly matters. We're making approximations today, and those approximations at times can be extremely bad. And I don't have much choice about it, so this is the kind of material that's on GREs and MCATs maybe, I don't know, I never took an MCAT. So I absolutely have to cover this stuff. But and of course, I'm going to be very clear where mistakes are made and how we tend to correct them. So again, big picture. Big picture is I'm going to put equations for stuff, and there's parameters in the equations, but here's the damnedest thing. The whole point of physical chemistry is to have all these equations that are completely accurate or so close to accurate that it's irrelevant what errors are there. And then you can say, okay, well, I want to know what happens when I mix these chemicals together, and then I plug it into the equation, and the equation tells me what happens. That's the whole point of PChem. That way, not only do I understand what's happening, number 2, I don't actually have to mix the chemicals together at significant savings, time, money, and waste, right? That's kind of huge if you can really do that. The equations I'm going to write all over the board have parameters that come from having done the experiment already. So the equation works, it's just I don't know what to feed the equation unless I do the experiment, meaning I'm working in reverse. That's why at times I think this part sucks. To be totally honest, I shouldn't tell you that I don't like this material, but I don't like it. I mean, I hate it. So if I start throwing up blood, call the hospital, for God's sakes, I've got fever or something. But I'm also angry. So, all right, liquid mixtures. What liquid mixtures come down to is partial volumes. And the big picture, by the way, is to start adjusting the numbers of the table in the back of the book, because I mentioned to you, if I'm going to get chemicals to react, I have to mix them together first. And when I do that, the numbers in the back of the book and the table in the back of the book are no longer correct. This is the first step in figuring that bits out. So the first thing you do is you start with partial volumes. And this is, wavy. What that is, you look at how the volume of a solution changes as you add something to it. And of course, we have to keep things constant, and not to be an idiot, we're going to keep temperature and pressure constant, which are relevant. And if I'm mixing things, then I must have something else present. I mean, pouring water into a cup isn't thermodynamically particularly interesting. Pouring ethanol into that cup, it's awesome. I should have brought it up. Let me give an example. So what? So you add a mole of water to a solution and its volume increases. That's boring. Let's add 1 mole of H2O into H2O. As boring a thing as you could do. If I add 1 mole of water into water, anyone tell me how did the volume increase? Huh? How many mils?
16, 18.
Whoever said 16, I'm looking for you, but 18, right, 18. So plus 18 milliliters. And that makes the designation for this in the book, we'll call this A, not BA, it gets a little hat, symbology anyway. Right, so water into water, I add a bowl of water, that's 18 grams, that's 18 mils, because that's how we define milliliter with the most common liquid we can find. Okay, example, 1 mole H2O into ethanol. Now, 18? That would be awfully boring. It's not 18, it's actually 14. 14 milliliters. So, now also let me point out that in this case, here I need to put that, okay, excessive amounts of ethanol. Right, so basically, I started with pure ethanol, I added 18 grams of water, I saw a 14 mil increase, but the ethanol is just not really diluted. Of course it is, but by such a small percentage, it doesn't matter. And you can imagine that as, so this is your extreme, so water into a pool of water, water to a pool of ethanol, and these are the changes. Now, of course, as I have half a pool of water and half a pool of ethanol, then the number is perhaps somewhere in between, but even not then necessarily true. Let me show you how that part works. Well, sorry, let me give you a formula for the total volume. After you've mixed things together, you might want to write that down. That camera? Did the camera do that? No. Okay.
It's on.
Cell phones, people, geez, see, I'm paranoid. Cat food. Okay, total volume is going to be this thing here. So now remember, I have this on the test. Oh God, my writing is here today. As in all things, but especially here and on the test, I can look at an equation and tell you in words that this equation corresponds to an action. And you're going to do that on the test too. I give you a de blah, de blah, de blah. De blah, de blah against de blah equals CP. And ask you, one of the questions is, tell me what that means in words. Tell a 5-year-old what's happening with this gas, right? So I can look at this equation and I can say in words what it means. It means that, let's say I'm going to mix, I got a jug of water, I got a jug of ethanol, and I'm going to mix them together. This says that the total volume will be how the partial volume changes as I add, and remember this is volume per mole times the change in moles, right? So I get volume, so the units work, the same for V. The problem is knowing what VA is, because it's going to be a function of the mole fractions, right? As you can see that here. When the mole fraction of water is 1, its partial volume is 18. When the mole fraction of water in pure ethanol is essentially 0, its partial volume is 14. In fact, let me draw it out for you. Again, probably, yes, I should PowerPoint sometimes, but I'm not. So this is going to be, all right, remember this symbol for mole fraction? I got this from the book, by the way. So, sorry while I'm just writing this stuff out. This is 58, and this is the mole. This on the right side. This is the mole fraction of ethanol, and it has units of mils per mole. Is that right? Yeah. I'll write that at the top. Yeah, because these are mole fractions, and then this guy. This is 14 And then this is the mole fraction of water. Sorry, the mole fraction. This is the partial volume of water. And it does some really weird stuff. So this is what water does. And then ethanol does like this. Anyway, okay, so that's ethanol. It's kind of easy to figure it out because water, of course, starts out at 18. So here, pure water, here, pure ethanol. And we started at 18 and ended at 14. But notice that the curves are just nuts, right? I mean, see, remember I was saying that it seems like the partial volume of water, depending on the competition, will be between 18 and 14? Yeah, for the most part, 18 and 14. But look, it does weird stuff. And this guy too, it's not like a line from here to here, which would be nice, because you could just kind of look at that and accept it. It's not, it's just nuts. And to fit that, I would probably have to just do some crazy Taylor expansion of some kind. Right now, my point here is that, sorry, let me bracket this off so we don't think these are to do with each other. My point is that this is how I get the total volume. And I got my container, because there's a party inside. I pour the water, and then I pour in the ethanol. It seems to me that I have to know what these functions are, right? They're functions, right? And they're Taylor. I get the data, and I fit Taylor series to them, and then I can give them the Taylor series. So it looks like I need to have a hell of a lot of information. I either need to have the data tables, or probably to fit this thing, or this thing. That would be a really long Taylor expansion. The more curves you have, the longer the Taylor series has to be. So it seems like to even know the volume of a simple liquid, I have to have a lot of information. My point is actually no. So, and again, I'm just walking you through this to understand how you can look at an equation and say in words, what is the action that this equation describes? It's not just a bunch of numbers. Now, let's say that I'm doing 50-50 by mole, which would mean a lot more ethanol, by the way, by volume. But anyway, 50-50 by mole ethanol. Now, do I need to know the curves for, I would have to know this half for water and this half for ethanol? Do I need to have all that data? Or do I just need to know these points? Which do I need to know? Because now remember, here's a way I could do this. I could pour in the water, and its volume is, if I poured in a bowl, that's 18 mils I just added. And as I add ethanol, its contribution at first dips, and then it rises. And so I need to know that as I pour in the ethanol. And then I add, I add a mole of ethanol. All right, so do I need all this information here? Oh, when of course water is also changing. Or do I need these 2 points? What do you think? 2 points? Just the 2 points? Okay, just the 2 points is right. You know why? Ethanol and water pour simultaneously. Right. The water goes in at the same composition the whole time. So just because I haven't poured out all the bottles yet, if I pour them the right way, as soon as the liquid hits the container, it's instantly 50-50. Meaning that I can just say, I can give you these data points, and then you figure, okay, well, here's the partial volume of water, and that's around 17, and you add in a bowl, so that's going to add 17, and right, and so this guy is going to add around 57 and a half, and I've added a bowl of that, so I have 57 and a half plus 17, and now you know the volume of the liquid. So my point here being is that I can look at this equation and say, I have a certain increase in volume, which is not 18, it's not exactly, you get these from densities, it's not exactly corresponding to the density of water or the density of ethanol, it's different, but these integrals are the action of me pouring, and I pour them in at the same time. Anyway, all right, kind of boring, kind of stupid, but here you go, that's how it works. And of course, the question is why? Why does this happen? It's easy. When I'm pouring water, what was I doing? I was doing, water into ethanol, sorry. It's, so why are you getting these crazy curves? There's 2 things. One, you're basically putting a round peg in a square hole, or vice versa, when you're pouring water into ethanol. It doesn't fit right. So that's the same thing as saying they have different molecular sizes. Sorry for again the shorthand. Okay, number two, they have different intermolecular forces. Okay, and ethanol and water, again, what gives all these crazy curves? For one, ethanol is bigger. Oh, sorry, ethanol is bigger. And you're putting in the smaller thing. And that smaller thing may be able to kind of sneak into the cracks that were already there. Because ethanol just doesn't quite fit together quite right. So, you know, if you have like, if you ever played with Lincoln Logs when you were little, and you had like, you built a little log cabin, you had the shingles for the roof, or just imagine a container full of straws, if they're all jumbled up, there's lots of free space in there. So maybe water is getting into those free spaces, and maybe that's why water doesn't increase the volume so much, because it's just filling the voids of the cracks of those big molecules that don't really fit well together. Okay, here's another big one. Now let's go to the opposite. Let's think of ethanol and water. Now water forms tetrahedra, right? I've got my oxygen with the two hydrogens, and I've got those lone pairs that other hydrogens like to stick to. And so water exists in these intermediate tetrahedra. As water flies around, it's always dragging two others on top and two others on bottom with it, in this nice little tetrahedral structure, and on and on and on. Now, ethanol can't form two hydrogen bonds, it can only form one. So that's disruptive. So it comes along, it hydrogen bonds to water, but it can't hydrogen bond to a second, like a water can. That's going to screw it up. So that might be why, you know, you get this crazy dip right here. When you get ethanol with water, it's disrupting those hydrogen bonds. How do you know? Have you theoretically modeled these curves? I don't have a clue. I have no idea how you do it. And other than you take the data, and other than we're going to write equations down for it. And here they are. These are from your book notation. And I'm not going to say too much about these. I will give you some example problems on the homework, and I haven't figured out yet whether they'll make it to the test. Okay, so this again is the partial volume. A sub I, change in N sub I. And of course we're at TP. And in here, I had to start making stipulations that N sub I is not equal to N sub J. It's awful. Now what that means is that I've got liquid A and liquid B and they're not the same. Right? Again, I'm mixing two liquids and they're not the same. That's what that means. If they're the same, that's water into water, and that means its partial volume is 18. That's boring. Right? There's nothing to really think about. Now what the partial volume is not equal to this. What I'm doing, I? Yeah, I'm doing I. This is, all right, the volume per mole. Again, let's say it's water. Now that's, if I'm calling that the volume per mole, that's not a partial volume. That's the volume of pure water, and the per mole tells me that. So that's for pure liquid I. So I know I should use A and B, but the book uses I and J. I should fix that anyway. Okay. So just notation. All right, now this guy's important because of this. What you're going to describe is what's called the mixing changing volume, which is now remember we're gonna just stick with A and B, but you can have more things. That's why I'm just going to give it a generic a sum over the liquids that are being mixed. In normally I'm just going to make it A and B. Now I'm going to have a certain number of moles of A and a certain moles of B. And so I have to multiply that by its partial volume. And at the partial volume, again, I'm not writing this as a function. I'll do the partial volume at the target concentration. So that'll work. And I'll just mix things all evenly at the same time. And I'll tell you about a question I once asked on the test. So there you go. So in that example I gave up here at 50-50 ethanol water, and I added a mole of water, I saw that is for water that was about 17, right? right? So this is 17 mils per mole, and I added 1 mole. This, what's this number? It's water again, per mole. 1.8? Yeah, 1.8, 18. That's it. I'm glad I didn't see who said that, because that's funny. Right, it's 18. Right, so I see that at the target concentration, this is 17. This would have been 18 mils per mole. It's all gets multiplied by 1, so water's contribution is -1. Then you add the same of ethanol. Now, as you can tell already, that this will not end up being 0. And again, because of those crazy curves, right? So anyway, so there's not much else to say about this. Just remember that this is out of the pure substance, again, water into water, ethanol into ethanol. And let me give you a question I once asked on a test, so I'm not going to ask it this time, but maybe I will, maybe I'll slip it into the final. I said, what does it mean that delta V mix is 0? Huh? What do you think? It means that the liquids don't change their volume when they mix. It's like they're the exact same liquid. That'd be like hexane and cyclohexane, something like that. Hexane and heptane, those are basically identical. So anyway, that's kind of an example of a question I could ask about. Just throwing this equation at you, which seems kind of simple, but giving you something a little bit to think about. Again, like what does it mean when when V mix is 0? Or what does it mean when V mix is huge? And that's like two molecules that have very, very different sizes. So what else can I say about this? Okay, so this is a physical quantity, and we'll get to pressure in a minute, but I can basically do all the thermo stuff. I can have mixing Gibbs energy. I'm sorry, right? And that's the change in Gibbs energy per mole. And of course, it's even T and P. And just remind me that I'm not mixing water into water. I'm mixing water into ethanol or something else. Again, that just means I'm mixing two things that aren't the same. And note that again, how do I interpret this? I look at the formation delta G of water, and that's great. It's for pure water. The point of this is that it's, and as I add a mole of water to a container, I would like to think that I'm adding that amount of delta formation G to the tank. Okay, there's no delta G inside the tank when the tank is empty, but I added a mole of water. I look at that data table, and it looks like I've added that much delta formation G into the tank. But the tank actually contains something else already. And that meant that its delta G in the table in the back of the book wasn't necessarily added. It was slightly different, which is what this thing is trying to tell you. And likewise, and of course, by the way, it does change. I actually I felt bad about pouring water into a cup and having you stare at it for a half an hour. So I actually brought a demo, so I'm going to show you that in a minute. A real demo. It actually does have water in it, by the way. So I have H's for the same damn thing. I's, and this is not to T and P, and Ni is not equal to J, whatever J is. I've got heat capacities, and again, the same thing. And I kind of don't want to write any of these anymore because it sucks. Let's see, you've got, sorry, I'm not working the board too well today. You also got mixing A's, you got mixing U's, you got mixing S's. And of course, I always have to have that little subscript because I have more than one thing in solution.
Why do you have R over the G in the differential? The bar over the G in the differential.
Sorry, because I'm an idiot. I meant to go there. Sorry about that. Sorry if it screws up your notes. Now, here's some interesting things. So standard relationships still apply. Okay, so the mixing entropy would still be minus the Gibbs energy of mixing with temperature, again at E and sub I. not equal to n sub j. So, normal stuff, the v, the partial of volume, the partial volume is the same as the change in the mixing g, constant t. And notice that I'm not keeping whatever I'm changing constant. That again, this notation, don't ever worry about this too much. I'm not really going to ever count you off on that on a test because it's stupid. Now with these quantities in hand, with this thing, which is generally all I care about, I'm going to define it just like I did there. So I'm going to write the same thing, so g's. And then I'm going to point out that g is h minus t delta s, but delta s is now the mixing delta s. And I got an example of that that's really kind of neat. Okay, so now that I've got the partial Gibbs energy, now I can see how that number in the back of the book changes. So this would be, what would this be? This would be, I look at the table in the back of the book and I see the formation G of water. Look at the table, I see the formation G of ethanol. If I pour them both into the bucket, that's how much delta formation G should be in the bucket. Energy should add. But I'm going to be off. So I can add those two numbers and get a result, but then when I somehow measure the G content of the bucket, I will get a different number that's off from the other number by this much. So this is its purpose. So again, ethanol and water. And this will be what happens if you didn't mess with the liquid to begin with. There you go. And notice that this is also equal to delta mix H minus T delta mix S. Now this guy is actually kind of useful. We're going to actually do a couple of things with it. Now, okay, so and also here's another two relationships that we're gonna use a little bit. Delta mix G, the change in mixing G with pressure is this. Again, these are like errors in the measurement. I should have measured this volume, but I didn't. Again, because of a round peg trying to fit in a square hole. Again, because I disrupted hydrogen bonds, stuff like that. Okay, so these relationships also apply. And so now here's, now let me start throwing actual examples at you. Let's say, what do I want to look at here? If mixing entropy increases, I'm sorry. Now, not all things mix. Hexane and water aren't going to mix, not ever. Even if you add a lot of soap, it generally doesn't work very well. So now what I want to try to do is start predicting whether two liquids will mix. Now, by some magical computer simulation, or the hawk tells me, I don't know, I'm told that liquids A and D, if they mix, will have a positive mixing change of entropy. Okay, now should I, and so if I keep that up, am I going to mix them better? Right, now think about this. Basically, I just said this is positive. Now my question is, should I heat it up to get them to mix if they don't mix? All right, if that goes up, this goes down. Put the minus over here, right? It's a little bit of a trick. All right, now does that help them mix or not? Yes, it will help them mix. Right. G goes down means that this happens, right? So that's a good thing. So, yeah, all right, so you can imagine, now you already know this. I mean, if I just didn't have these symbols, it's another example of the fallacy that you have to kind of get over. If I just gave you without these delta mixes, and I said, okay, entropy is always positive, so should you heat this up? And you would have said yes, but you got it a little bit thrown off by that. But that doesn't mean anything, right? especially if you're speaking Russian, I'm using the wrong alphabet. So now you can imagine that since entropies are always positive, if two things don't mix, you should heat them up. Is that right? Entropies are always positive. Therefore, when two things don't mix, I should heat them up. Is that correct? Good.
Sometimes.
What a good guess. Always positive? Right? Right. This is not a trick. Do this. Do this. All right. Always positive? No, not always positive. So you don't necessarily know which way to go. I should be a rapper. So let me give you an example. Example A and B. Sorry, I'm just looking at time. Okay, now let's take triethylamine and water. Now here's one way to think about this. Let's just say that we're talking about not the whole thing. When these equations, by the way, they apply to the liquid mixture as a whole, not to the components, not to each component, just so you know that. But let's think of it, let's imagine that it did. Let's add triethylamine and water. And if I add 5 mils of triethylamine to 5 mils of water, I'm going to get 10 mils, well, about, maybe a little bit more, maybe a little bit less, but let's just say, for argument's sake, it's going to be about 10 mils. Now, if volume increases, does entropy increase? Yes. And you learned that for a gas. This ain't a gas. Right. Now, normally volume increases for triethylamine. So here's the water, here's the triethylamine, its volume increases, so the triethylamine is now in this big volume. And if it was a gas, that'd be fine. And gases always mix. But let's do a negative. A picture. Let's do a picture of what a negative mixture would look like. So again, I added triethylamine and water. So let's say A is the triethylamine. You see to fit inside the water, because if it doesn't fit and maybe it doesn't hydrogen bond, A has to bunch up like this. And the B's surround it. You know, the B's are like this. And the B's look like they're lining up around the A's. Okay, this is order. Okay, so I can see here that if these two things mixed, while they do have this bigger cage, which is good, that's not a trick, but locally, they actually had to order themselves just because they had no choice. Kind of like how my one cat dominates my other cat. The dominant cat tells the other cat what to do, which is a bit of a problem. But so A doesn't have a choice to do this. So A is losing entropy, which is bad. All right, versus not mix at all, which is A's over here, B's over there. It's a form of apartheid. So the A's are over here, and the B's are down here. Right? They don't mix. But look at all the entropy you got. Right? So this has less entropy, and this has more. So delta S is negative, delta S is positive. There you go. Delta S is positive is good because delta G is minus T delta S. So that's an example. Now let me draw an energy diagram. You get used to this, you're going to see this one a lot. What I'm going to do is plot. So what I like to do is when I try to figure out whether things mix or not, I like to analyze it like this. This is very useful. And so let me make sure I know what I'm doing. I'm going to have energy in kilojoules per mole on the y-axis. And I'm going to have, I'm going to talk about A and B mixing. I'll make this chi B. Again, remember chi are mole fractions. So I'm going to do this a lot. I'm going to make B a solvent more often than not. Okay, now let's do this for a positive, negative, right, a negative, so this is for a negative, or negative delta S mix. And actually I have numbers here. Sorry, Sorry, I'm going to put the 0 a little bit higher. And this is about minus 4.1. Now I'll tell you where I get these numbers. Of course, we're going to be solving equations. Okay, if delta S mix is negative, depending on the temperature, then it's going to bow downward. Okay, sorry. T delta mix. Okay. Now, again, does that help or hurt mixing? It's saying that you're losing entropy to the system. Right? Help or hurt? You added two things together because you wanted to mix. I'm asking you, does this help you mix them? No, this is not helping. This is actually making delta G become positive. Why? Delta G is H minus TS. Negative mix, temperatures are positive. This is hurting you. It's not mixing. Okay, so are you doomed? So I told you the system is losing entropy. That's bad. But are you doomed?
No.
Why? Is there other entropy? What did you say, gravitation? Is there other entropy? See, I don't look at this like heat. I see this as entropy, because entropy is everything. This is the entropy of the surroundings, system, right? No, there's no subscript. That makes it system. This is the heat of the surroundings. So if that sucker does like this, and delta mix. Now remember, this minus that, sorry, this isn't the best drawing. Okay. So, they will mix. They'll mix in this case because the entropy of the surroundings increased such that the loss of entropy to the system was overwhelmed. Not by a lot, though, not by a lot. These things mix, they don't mix well. They still, well, it either does or it doesn't. Now, what would I do to this particular system? And again, this is triethylene and water. Don't write that down, I won't bring it up again. I bet I can unmix them. How would I do it? Now we can't really mess with this guy. But what about this guy?
Heat it up.
Huh?
Heat it up.
Heat it. Have you ever seen heat unmix a liquid?
Yeah. Well, yeah.
You're supposed to say no.
Oh, no. Oh.
Triethylamine and water. There we go. All right, if you can't see it, here's the camera. All right, you see, hopefully the camera is doing a good job. You folks can see it. It's mixed, it's a little cloudy. It's a little cloudy, but it's clearly one liquid. All right, you folks see this? Again, this is exactly that system I just showed you. I know some of you can't see it on the top, but the people in front will vouch that is one kind of yellowish liquid. And so while I'm blabbering on and on, I'll pour it with my hand. And I know it's an amine because of the slightly brownish color. And anyway, so while I'm warming it, sorry, it does take a minute or two. Oh, no, it's starting to. All right, you two can see it. You see some swirls starting to, all those bubbles. Yeah, it's starting to look like when you mix like two liquids together and it's cold. It's like syrup, like mixing syrup and water. Anyway, here, let me just find out the board. And again, I know you guys on top can see it, but I'll put it into the camera so when you watch the video, you can see it better. All right, now, this example I'm doing is this is what you call a non-ideal solution. So let me tell you what an ideal solution is. Ideal solution. Okay, now, I know there were times I accidentally called a perfect gas an ideal gas, and that was very much wrong of me. So an ideal solution is for liquids what a perfect gas is for a gas. And so some of the concept of perfect gases not interacting and not having volume are adjusted for ideal solutions. Kind of the same ideas. One issue is that you have, see that? See that? Yeah, oh, yeah, see, I got in the mix again. Okay, just wait a second. Anyway, so ideal solution, oh, look at that, just by warming it in my hand that 1 second. Oh, now I can't make it, it's over. It's too warm. So, they're unmixed. I'll just give it a second and I'll put it to the camera again, but now it's done. I warmed it up too much. And so that T delta S is now gone underneath delta mix H. And that's it, it's done. It won't mix again. So I'll show that again in a second. We'll come up after the show. Here, I'll leave it up here so you can check it out. Okay, so anyway, an ideal solution. So what do I want to do first? Sorry, I didn't prepare as well as I should have. And I think I want to just point out some things about gases. Liquids, and vapors. Okay, to start to get to the thermodynamics of mixing, we're going to do something really funky. We're going to borrow the vapors of the liquid. As I mentioned before, my cup of water does eventually evaporate because some of it is in the vapor phase and the wind blows it away, and then the whole process repeats. So I'm going to actually start looking at gases again because I'm familiar with that. And then I'm going to do some clever trickery to get to the thermo of liquids. So I'm going to do it by looking at gases. So I'm looking at vapors. So I'm not calling them gases, I'm going to call them vapors because that's kind of the correct word for that little bit of, I put my nose over water, I can smell water. You know it's there, especially if it's salty water or if it's like Coke or Pepsi. And then this is equal to M sub A RT, because we're at constant temperature, we're at constant pressure. Okay, that's dGCP. I'm going to come over here in case you're having trouble seeing. So of course delta, sorry, my handwriting is bad today. M sub A is going to be the integral from the initial to the final. Change in G sub A. And that is going to be the integral of pressure. We're going to bring pressure over here. We have a bunch of constants that don't matter. Change the pressure over pressure. And that would be the initial pressure and the final pressure. And therefore, delta G sub A. This should be child's play at this point. And I'm just doing this for a gas. Okay, again, my point here being is that I've just done something we've done many times for gases. I'm just calling them vapors now. That's the only change. And what does that matter? Also notice that if I make these volumes, I pick up a minus sign, and delta G is now the isothermal change in reversible work. Right? So remember that stuff because that's on the test. So now here's what I want to say that is when I have my I don't have my cup of water. If I have my cup of water and I put my nose over it, I can smell the water because it has a certain partial pressure. Now, if that vapor is mixed with another gas, and let's say it's a gas I can smell, its partial pressure goes up or down. It would go down. I mixed it with something. All right, now, so let's think about vapors mixing. And then I'll explain why that's the same thing as the liquids mixing. Wait a second. What would I call PI? So if I'm going to think about vapors in my example, that would be the partial pressure. Let's do water. I have a cup of water. I'm going to dilute it. And before I dilute it, I smell the water. I measure its pure partial pressure. So the initial pressure before I mix vapors is going to be this. So this is A, and that's its pure partial pressure. Pure partial pressure. Okay, so that's just the amount of vapor in the air. But now I'm going to mix that vapor with something else, and then I have to stop. And once I do that, the final pressure will just be the partial pressure in a mixture. The partial pressure in a mix. Okay, so where did my eraser go? All right, now let's put it all together. That's for A, but my point is that I'm mixing two vapors. And I'm trying to get the delta G for mixing two vapors. And then we'll take our 10-minute break. That means that delta mix G is going to be the sum of them both. So I've reduced the partial pressure of A from its original pure partial pressure, because I started out with the pure vapor, but I messed it up and lowered it because I introduced B, another vapor, which summarily had its partial pressure reduced from its pure liquid state. Now my point is that this is all again for vapors. But now if I divide by N, the total number of moles, what's dG over N is what? It's what we've been talking about the last few days. What's that? Chemical potential. Now the chemical potential. What's N sub A over N? Right, how much of A is present divided by the total, number of moles of A divided by the total number of moles is what? Mole fraction, right. Chi sub A, RT ln A. I know I've gone over, so we will take a 10-minute break. So we'll start a little bit late. And unfortunately, I'm going to continue yammering about this stuff, which sucks. Sorry, my handwriting is bad. Okay, so now this is a little different, looks kind of the same, and so what? G, chemical potential, the G per 1 mole, what does that matter? You take G and divide by 1 mole, that doesn't do anything. Fine, all right, so this is easy, but let me ask you this. I've poured my ethanol and water mix, and before I drink it, which I'm going to do when I go up, never mind. Before I mix it, I mix it before I drink it, are the vapors and the liquid in equilibrium? Are they? Well, I mixed them, I set it down, and I waited a day. Now, I know that there's some ethanol vapors and some water vapors, because I can smell it. I can smell it on me. But I can smell it when I do this to the cup. Are those vapors in equilibrium with the water? Yes. Yeah, I'm worried about when they'll put it in the little box, all right? Now, are the chemical potentials the same then? What defines equilibrium? Equal? Right. So if the chemical potentials of the vapor change and the chemical potentials are equal, then the chemical potentials of the liquid changed just as much, right? Right, now how much vapor do I have? A lot? Here's the cup. Do I have a lot of vapor? No, most of it's in the cup. But does that matter for chemical potential? No, I divided the mass out. Right. So here's the trick. I'm going to take what I know, this is perfect for vapors, and then I'm going to say, because this is chemical potential and the liquid and the vapor are equal, those numbers have to be the same. And no approximation, by the way. Now this is 100% true of vapors, and then I'm going to say, if I can measure the partial pressures of my ethanol and water before and after mixing and put them in here, I know exactly how much the chemical potentials changed for water and ethanol. And by the way, I mixed 1 mole of each, and so now I know delta G2 is the same number. Huh? We okay? All right, guys, I know I went over by 5 minutes, so a little extra time. Smoke them if you got them. Don't let them steal.